Welcome to this explainer. Today we're cutting straight through the binary noise to master modern IPv4 subnetting. By diving into our sources, we're going to uncover the practical skills you need to seamlessly architect networks and, more importantly, save you from those costly, resume-generating network outages. So, here's our game plan for today. First, we'll look at IPv4 structure and masks. Then, we'll tackle classful versus classless routing, variable length subnets, the incredibly fast magic number technique, and finally, how to avoid some of the most common subnetting mistakes. Let's get right into it. Section 1. IPv4 structure and masks, the absolute foundation. At its core, subnetting is just the practice of dividing a single large network into two or more smaller, highly efficient subnetworks. We do this by simply borrowing bits from the host portion of the IP address. And the primary motivations here? Well, it's really about performance and conservation. You want to contain broadcast traffic so your network stays lightning fast, and you absolutely have to allocate your limited IP space efficiently. Think of a 32-bit IP address in two practical parts. It's kind of like a physical address. The network bits represent your street name, identifying the broader network, and the host bits represent your specific house number. The subnet mask acts as the definitive dividing line between the two. All those continuous ones in the mask, that's the network. The zeros, those are the hosts. When we subnet, we are literally just moving that dividing line further to the right. Moving on to Section 2, classful versus classless, solving the waste flaw. You know, early on, the legacy architecture forced IP addresses into rigid Class A, B, or C blocks using fixed-length subnet masks. But as the internet completely exploded in the 90s, we realized pretty quickly that we needed a much more scalable solution. So, in 1993, classless interdomain routing, or CIDR, was introduced to allow for variable sizing, which then evolved into the VLSM standards that we use everywhere today. That old classful system was hugely inefficient. It assigned massive blocks of IPs based entirely on just the first octet of the address, regardless of what an organization actually needed. A Class A network handed you over 16 million hosts. A Class C gave you 254. So, here's the crucial point. Think about this. What happens if you just need two IP addresses to connect a simple point-to-point router link? Under those old fixed-length class rules, the absolute smallest network you could possibly assign was a Class C. That means to get the two addresses you need, you instantly waste 252 usable addresses. No way around it. You can see how this rigid architecture would have exhausted the global IPv4 supply almost immediately. Section 3. Variable length subnets. Changing the game. According to our sources at Practical Networking, VLSM is essentially the subnetting of subnets. It's a total game changer. It allows network engineers to divide IP space into a hierarchy of subnets of vastly different sizes. You're no longer locked into those default /8, 16, or 24 masks. You can perfectly right-size your networks. It's really amazing how a single router can take a much larger block of IP space, something like 172.16.0.0, and meticulously carve it into smaller, specific interface networks. By breaking it down into multiple /24 subnets for different Ethernet interfaces, you're tailoring the network directly to the physical topology of the office. And expanding on that, VLSM lets us map out highly efficient network topologies. Point-to-point links between routers only get the exact tiny subnets they require, like a /30. Meanwhile, the local area networks branching off those routers can be sized as /28s or /26s, depending entirely on user counts. This leaves the rest of your IP block beautifully preserved for any future expansion. All right, Section 4, the magic number. Fast math in the field. Enter the magic number technique. Now, subnetting is very often taught by making you painfully convert dotted decimal into 32 ones and zeros, draw a line, and convert it all back. Forget that. The magic number technique cuts straight to simple decimal math, so you can calculate your network boundaries in your head in mere seconds. It is the ultimate cheat code. Here is the process. It's incredibly straightforward. First, look at your subnet mask and find the interesting octet, the one that isn't 255 or 0. Subtract that number from 256. The result? That's your magic number, which also happens to be your block size. So let's say your mask is 255, 255, 255, 192. Just subtract 192 from 256. Your magic number is 64. To find your network boundaries, you literally just start at 0 and keep adding 64. So your networks start at 0, 64, 128, and 192. It is really that easy. To truly master this in the field, memorizing a basic CIDR cheat sheet is an absolute must. You should instantly know that a /26 mask, which ends in .192, gives you a block of 64, and therefore 62 usable hosts. A /29 gives you 6 usable hosts, and a /30, that perfectly fits a 2-host router link. Having these specific sizes locked in your memory is a major trick of the trade for top-tier network engineers. Which brings us to Section 5. Avoiding mistakes in preventing network outages. You definitely want to watch out for these exact pitfalls. Number 1 is the off by 2 error. Always remember to subtract the network address and the broadcast address from your total host count to get your actual usable hosts. Another huge one is sizing with no headroom. If you squeeze 30 devices into a /27, I guarantee the very next printer you plug in is going to break the network. And finally, overlapping subnets, especially when you're setting up VPNs with a partner company who just happens to be using the exact same private RFC 1918 address space as you. Let's test this out with one of the most common configuration errors. Imagine typing away on a router and you try to configure an interface to be the start of a network at 192.168.1.32 with a /26 mask. Why exactly would this cause a total network failure? It all comes down to misaligned boundaries. As we just learned with our magic number, a /26 subnet means the mask ends in 192. Subtracting 192 from 256 gives us a block size of 64. Subnets absolutely must start on a multiple of their block size, so your magic number of 64 dictates the network can only start at 0, 64, 128, or 192. That IP address, .32, it's sitting squarely in the middle of the first subnet. It's completely misaligned and the router will flat out reject it. Before we wrap up, let's fast forward just a bit to the future with IPv6. IPv6 changes the subnetting philosophy entirely because it completely removes address scarcity. A single standard /64 subnet in IPv6 contains this absolute mind-bending number, 18.4 quintillion addresses. With numbers this insanely large, the entire optimization game just vanishes. There's no VLSM, no stretching IPs, and no subtract by 2 for broadcast addresses. You simply size by organizational structure, not by host count. Which leaves us with a pretty fascinating thought to take away. As IPv6 adoption scales globally and the need to tightly conserve every last host bit entirely disappears, is the intricate mathematical mastery of IPv4 subnetting destined to become a lost historical art? Well, until that day comes, the magic number will keep your networks running smoothly. Thanks for joining me on this explainer and keep building great networks.